I want to thank you all for coming to my paper presentation. My name is Ekaba Bisang. I'll take a few seconds to thank my supervisor, Dr. John Ume, who is the Chancellor's professor. Everything I have learned in this field is because of him. He has also been a close friend and almost like a father figure to me. Thank you very much. My talk is going to be on optimizing self-organizing list-on-list using transitivity and pursuit-enhanced object partitioning in the context of non-stationary environments. In particular, we will speak about hierarchical singly linked list on singly linked list, and we will capture the locality of reference using the so-called object migration automaton. Data storage and processing are fundamental twins of computing, and these are also critical in the area of artificial intelligence, which is getting more and more prominent today. The goal is to enhance the speed of data retrieval, which is what we are concentrating on. In particular, we will speak about non-stationary environments. Non-stationary environments are those which the distribution change with time. And if you try to use learning schemes with fixed policies, these are not beneficial. So we will speak about two types of non-stationary environments, which are the Markovian and periodic switching environments. We will also speak on the query generators. In other words, these are the generators which provide the queries under these two distributions. The basic paradigm that we use is the environment and the automaton working in a closed loop. The automaton chooses an action, say alpha n, and the environment either rewards or penalizes it. Let's say beta n. The environment is doing this using a probabilistic mechanism, and the aim is that the automaton learns the best action which the environment provides. In our particular case, what we would like to do is to minimize the expected penalties that we are receiving over the course of the entire quote-unquote experiment. The point is, can we minimize the query accesses for data structures in non-stationary environments? Fundamental to this study is the field of adaptive data structures. There are two important rules in this context. One is the move to front rule. Here you have a list and the element 7 is accessed. It is moved to the front of the list. 3 is then accessed. It's also moved to the front of the list. This is the traditional move to front rule, which has been around since 1968. As opposed to this, we have the transposition rule, where 7 is accessed, it is moved one step to the front. 3 is accessed, it is also moved one step to the front. The move to front rule converges quickly, but not with such high accuracy. The transposition rule converges slowly, but gives a remarkable high accuracy. Our aim is to try to merge these two, and we are going to do this by using list-on-list. The list-on-list paradigm is very simple. We divide the entire list into sublists. These are the sub-context, and this is the overall list context. So when an element is chosen, for example 8, it can be moved to the front of the list within the sublist, and then the entire sublist can be moved to the front of the original or of the overall list. So we can either have a sublist being moved in the move to front or transposition way, or the element within the sublist being moved in the move to front or transposition rule. So this leaves us with 4 interesting rules: the move to front, transposition, and the TR-MTF and the TR-TR, where the first is the move for the sublist for the element rather, and the second is the move for the entire sublist context. So the problem with this is, if we have a particular list as a sublist, and then we move the element using, say, the move to front rule, as in the figure, these elements are always going to be in the same sublist. So the initial configuration will still be the final configuration, which need not be the case. As a result of this, the list organization is always worse than the original rules. For example, the original MTF rule for the exponential distribution has a cost of 8.68 units, whereas the MTF was 24.78. All of these are always worse than the original rules. And the reason for that is because the elements which were put there originally stay there statically to the end. So the aim of our work was to try to move the elements within the various subgroups so that the elements which should be together are found together. The way we do this is by invoking the object partitioning problem. Here are three groups. The grouping on the left, the extreme left, is the true underlying partitioning, how the elements should be partitioned. But because we don't know it, we initially partition them as shown in the middle. Our aim is to move the elements within these partitions in such a way that we converge to a final partitioning seen in the left block. And it will be ideal if this partitioning is the same as the original partitioning. If we can succeed in doing this, then these will be the elements in their respective sublist. This is done by a method which we have called the object migration automaton. This has been the benchmark for more than 30 years. The idea is also very simple. If we have two objects that are accessed together, if they are in the same sublist, then reward them by moving the objects towards the internal state. This means that we are very confident that they belong to the same group. However, if the objects are in different groups and they are accessed together, this means that the places where they are should be penalized, and they are penalized by trying to learn to go towards the opposing groups. The special case, of course, is when one of them is in the boundary state. In this case, the object is moved to the other class, and one of the objects apart from that is moved back to alpha G to make sure that the number of objects is the same. The OMA was found in 1987, and since then there are many enhancements to that which we have now incorporated. So our aim is to incorporate the learning of the groups by the enhanced OMA, and then we use the pursuit concept and the transitive pursuit concept, which we will tell you about, and get much better performances. The experimental setup we have used here is uniform for all the algorithms. It has 128 elements which are split into R groups from 2, 4, 8, 16, 32, 64. And we have done 10 experiments on these to perform the averages, and then 300,000 simulations or queries from each of these. The metrics we have used is by using the asymptotic and amortized costs in Markovian and periodic environments. And we have tried to look at the rate of convergence with respect to time. So these are the results. The enhanced OMA is nothing but the OMA, except that it takes into consideration the final convergence criteria. And from the results we have, we can see that for the ZIF distribution, it takes 43.35 units to assess it, whereas the MTF takes 19.14 units. So you can see that there is a marked improvement, and the same thing happens for the periodic switching environment. The MTF takes 49.64 units, whereas in the elements, when we use the MTF EOMA, it takes just 14.63 units, also a marked improvement. And it turns out that If you take into consideration the joint accesses of two elements, then those which should be in the same group cluster together, and those which should be in different groups come with variable probability. So we can now take a particular threshold and say that by taking the joint access probabilities, we can have a certain certainty that these query pairs should be within the same groups. And then we can augment the OMA using this concept, which is called the pursuit concept. The pursuit concept has been used in learning automata, but now we use it in object partitioning. So this leads us to the PEOMA. The details of it are in another paper. But when you look at the result, you find that in the ZIF distribution, where the cost was 43.35, with the PEOMA, we have only 5.8 accesses on the average, which is almost on a factor of 8 to 10 times the previous. The final way in which we have augmented the learning of the groups, which is the focal point of this paper, is by using the property of transitivity. In transitivity, what we mean is if we know that OI and OJ should be together, and if we know that OI and OK should also be together, without any accesses, we can infer that OJ and OK should be together. So just like before, we can use the pursuit concept, but without any additional queries. We can make use of that information to tell us which objects should be together. This leads us to the hierarchical scheme pairs with the TPEOMA, which is the Transitivity Pursuit Enhanced Object Automata. The results again, without going into the details, are here for the ZIF and the exponential distribution. Now the bad news is that it appears as though for the transposition, as though for the periodic environment, the transitivity property is not quite advantageous. And the reason is that when the queries come together, we can make use of it as we did for the PEOMA. But the inference of the transitivity doesn't seem to have an effect on the query accesses. We don't know why this is the case, but that is what it is. But generally speaking, our results give a good performance, especially when the outer least context was the MTF. So you see for the ZIF distribution, the MTF was 43.35, but the MTF TPEOMA was 13.45. And we see the same superior performances across board for the Markovian switching environment. However, for periodic variations, the performances were inferior. So we do not recommend it whenever we are working. We do not recommend a transitivity pursuit augmentation to the hierarchical schemes when we are working with periodic environments. But as you can see, our methods are superior over time when compared to the de facto MTF and transposition rules. So we conclude that what we have done is to design adaptive data structures which minimize the asymptotic search costs in non-stationary environments. We've introduced the concept of list-on-list and used the state-of-the-art object migration automaton reinforcement schemes to learn the clustering of the queries and then invoke those to actually perform the sublist movement. The results almost across the board show superior performances, except where we have the transitivity criteria in the periodic environment. The conclusion is that the TPEOMA hierarchical schemes have suitable performances but are not recommended for the periodic switching environment. As far as we know, for list-on-list with singly linked list, what we have provided are the state-of-the-art data structures for non-stationary environments. Thank you very much.